All right, welcome to 2.4 where we're going to talk about and or inequalities. And what we need to learn early on is, what and or do because the algebra, maybe except for this bottom one here, shouldn't be too wild. In fact, I don't even have any algebra. It's just, hey, let's compare those graphs and see what they do. But really, this one equation, even though they're sandwiched together here, nothing algebraically is going on too crazy. It's still just some basic chapter 2, um, you know, stuff we've done so far. We just need to understand, well, what does it mean for and or, and how do we solve two equations at the same time? And so here's where we get my, not true textbook definitions, but they make the case and they work. So the idea is that and is maybe the words are exclusive or demanding. And in fact, to say and is demanding, maybe that makes it stick in your head because it kind of rhymes. So and is demanding, but what does that mean? It means both of the equations must be true for some value to be true together in the final solution. That's why I underlined it. Again, this is very informal ways of saying it, but I think it helps click for the students. It's saying both individual ones must be true to get a true out of the final. Now, or is allowing. So again, and demanding or allowing, they kind of have some kind of rhymes in there. Hopefully that helps you. And what I mean by allowing is either equation can have a true, and then it's true for the entire equation or both of them put together. Now what we need to do is we need to figure out what does that mean graph-wise, and we need to actually look at a few different cases here. Here's case 1. Case 1 is that I've got a graph, I don't know, maybe here's 0, here's 2, and then here's -3. Let's say that my first equation looks like this, and my second equation, looks like this. So equation A, equation B. Now, if I look at those two graphs, right, because at some point I'm going to solve both of these and they're both going to have their own graph. If I were to say, what is the and solution? And is demanding. And requires both of these graphs to be true in order to be true for the final. Now, what does that actually mean in practicality for the graph? Well, here's -3. Here's 2. Now, what we mean by it's true for both is it means I graphed the same section for both of them. And where do I graph the same section? Or here's finally the key word is where do I have overlap? From -3 to 2 with the bracket is where I graphed both of those twice. So that would be your and solution. It's the overlap where both of those were graphed. That means they were true for both. That's what it means to be true, is you actually drew the graph over some section. And wherever you have two sections overlapping, notice that the parentheses stays from one and the hard bracket stays from the other in that case. You don't switch those symbols. You keep them as they were if you have to write them. The and, again, takes where they both showed up or they both started overlapping. Now the or solution, this would be actually kind of interesting, is going to be quite different. Here's -3. Here's 2. I'm running out of space a little bit here, but the or solution is where either of these are true. And here's the way I'm going to say that, and hopefully you can catch what I'm going to say here is that equation B can be 2 or less, or another way of saying it is equation B can be equal to or less than 3. It can be, -3. It can be equal to or less than -3. It can be between -3 and 2. And equation A can be between -3 and 2. And equation A can also be greater than 2. Now, if you think about it, that's everything. Every number is either less than or equal to -3, between these two values, or greater than 2. So for the or equation, you actually just select the graph that had a giant line going all the way across for each of them. So you get two completely different results. Or is allowing. It's generous. It says, hey, was it true somewhere? Then it's good for both. And in this case, because I overlapped and went to the left and went to the right, everything was covered by the OR equation. But again, the AND is demanding. It says you got to be true for both. Chop off anything else, so to speak, that wasn't a part of both of them, and then collapse them together. Let's look at another example here. So let's say we had something like this. Let's say that was, 7 and 12. So whatever we were solving at some point, one of my solutions was 7 or equal to and above, and then greater than 12. Or greater than or equal to 7, and then greater than 12. Now in this case, this is going to be interesting again. For the AND solution, I've got my 7, I've got my 12, and it's only where it's true for both. And remember what I also said about AND is you start using the same symbols of wherever you started overlapping. And where I started overlapping is actually right here. There's your AND solution. So it's only where the two graphs start to share the same information, and they start to share at that open parentheses. So copy that symbol and then draw the rest. The OR, again, is what we call allowing. I guess I'll put a box in it already. So it'll take where either of them are true. So was it true for one of them, then it's true for both of them. Well, this is a little bit interesting. The 7 or above, actually, think about it, covers and gives a little more than the 12. So if it just needs to be true for either of them, what's kind of weird about this is that the 7 or above is the only thing you need to draw for your final answer, because it already covers everything the other solution is going to bring to the table up top here. So 7 and above covers both. There's no use of drawing two different graphs if one technically says everything that it needs. So this is a pretty funky example because, we ended up in this odd scenario where it's almost like you graphed one or the other, which is kind of a little interesting. But again, it's because the AND has to be overlapping for both. The OR says where was it true for either, and the first or top graph makes it true for both. It has 7 to 12, and then that other graph, well, it's not giving anything new because it went to 12 and beyond anyways. And maybe that's enough, but there are a few other scenarios we could draw out, but I think that's enough to get a start, and maybe we'll see the others as we go through. So let's look at our examples now. I'm going to speed through this algebra really, really quickly. You'll add the 1 to both sides. That's 4x is less than 6. That's x is less than 3 over 2 when I solve it all out. Still write the and in between. Over here, I just need to subtract the 6. And I'll cut to writing it on the bottom. That'll be x is greater than negative 4. So automatically, there's my answer. Now there's still set builder notation, and just be careful about the direction the x is going. But let's dive on to the graph solution and the interval notation solution, because so far we were just looking at graphs, but we will need to write some interval notation for this as well. So what I'm going to do is I'm going to draw the two individual graphs. Let's see here. There'd be negative 4. 3 over 2 is just 1.5. I'm going to draw the two graphs up above and the final graph below. So if x can be less than 3 over 2, less than 3 over 2 is over this way, parentheses because I can't be equal, and x is greater than negative 4, greater than negative 4 is this way, can't be equal to. And so hopefully from looking through our examples, this looks a lot like the first one. Your final answer would just be this for your graph. So from negative 4 to 3 over 2, parentheses for both because that's what they each had, and we're done. Your interval notation, again, would be pretty simple. Your interval notation would just be parentheses, negative 4 to 3 over 2, because that is your least to greatest, comma, everything in between values. Notice I used parentheses, again, to match the graph that I drew above. So not too bad on that one, pretty easy. Up next, for number 2, what we need to see here is what does it mean when I have these kind of double inequalities at the same time? Well, you can just kind of solve these simultaneously. I can choose to add 1 to all sides. And now I have 6x is less than 36 is less than or equal to 1. I can then just divide all sides by 6, which will unfortunately leave me with 1/6 on the left, but x is by itself. And then 6 on the right, because 36 over 6 is just 6. Now at that point, that's my answer. This is still an and inequality. Let me kind of draw a line just to space that out. But let's see what we can do about this, or figure out how to rewrite this. Usually when we write our and inequalities, or we work with inequalities, it's nice to maybe write this out as 2 separate equations. You can do that for the first one. Again, the alligator's mouth was opening to x and away from 1/6, so if I rewrite that with the x leading, then it needs to look like this to still be true, right? Alligator opening to x, 1/6 it's pointing away, done. I could then write and my second equation is written in correct order anyways, so it's just x is less than 6, and we're good to go. So that's the other way you could write it. Really quick then, what's your graph going to look like? Well, here's 0, and maybe here's 6 over here just for some scale. And this graph should be pretty easy, and actually, when you have it this way, this is really convenient. This is saying, hey, 1/6 is about right here. You know, right next to 0, it's actually probably closer. And then I can go all the way up to 6, but I just can't be 6 exactly. That'd be your graph, and your interval notation would, of course, be 1/6 with a hard bracket, and then 6 opening up. Right? It's almost more convenient when it ends up being written like this, because it's kind of showing you that really quickly. It's saying, hey, from 1/6 and anything you want up to 6, that's your graph. And then there's interval notation saying the same thing. Of course, you could graph these both separately. You know, I can be 1/6 or above with a bracket. I can be 6 or below, but not 6 exactly, parentheses, and then see where they overlap. Same idea. All right, that is our 2 and inequality examples. The one thing I do want to maybe point out, because it didn't show up here, is it showing up on the back? Let's maybe look at one more scenario, just because I think we need to cover it. Let's say we had x is greater than 7 and x is less than 4, just to go through that case. If I had that, I would have 4, I would have 7, I would have x is greater than 7, maybe we'll do or equal to, x is less than or equal to 4. Maybe let's not put it there yet, and now let's answer what would these 2 graphs look like. Well, here for the and, here's what's interesting. The and is no solution, because there's no spot these graphs overlap. And for the or, we do one more thing that's a little interesting. We have 2 complete separate pieces, and remember that for or, we say or is allowing. Either piece can be true, and then it's true for both. So I need to essentially just keep both pieces. Now what we'll see is in interval notation, we union them. Now that's not a capital U, it's a special symbol that you'll see on your homework, but you choose this union symbol and you actually connect both of those. You know, if this was interval notation, it's from negative infinity to 4, and then it's, parentheses, same symbols, from 7 to infinity. Because my graphs are split into 2 chunks, my or will still have those 2 chunks. You know, again, these are small representations of those graphs, and we use this big U symbol to say, yeah, these aren't connected actually, but they are connected because or says they can be, if that makes sense. You're saying, I know the graph is split, here's a symbol to say I know it's split, but I still want these 2 to be a part of my final answer. All right, well, let's look at these 2 other examples really quick. We've got 0, -3, -6. This one says x can be greater than -3 with a parentheses. This one says I can be less than or equal to, so there's less than or equal to, Hey, look, it's a good thing we just did that last example. So this would again be that same scenario. I can go from negative infinity up to negative 6 with a bracket, or, and again, and union, my graph's in two pieces, but connect them, they're both now valid, from negative 3 to infinity. Again, just remember that if this were an and inequality, your answer would be no solution. There is no graph you select, it's just the blank graph. And then your answer is there is no solution. I can't even draw interval notation. You just, say no solution. All right, last but not least, we've got some algebra review, essentially, right? At this point, it shouldn't be about the or and, it should be about the or and. This should just be a little spot for us to review some algebra we've dealt with in the past. So let's go ahead and start distributing. Negative 4 to x will be negative 4x. Negative 4 is positive 16. There's a negative 2. And there's 6. We'll copy the big ol' or. And then now, distribute again. I've got negative 4x. I've got negative 8 plus 10 is greater than or equal to negative 7. So far, again, just to say it out loud, all I've done is I've just done the distributive property. Let's combine our like terms before we start moving stuff around. It's going to be negative 4x plus 14 is less than or equal to 6. Still or. And then that's negative 4x plus 2 is greater than or equal to negative 7. All right. Again, I'm solving both as I go here. So the next step would be to move over the 14 and move over the 2. So now I've got negative 4x. If I move over that 14, will be negative 8. On the other side, still or. And then on the other side, I've got negative 4x is greater than or equal to negative 9 by the time I subtract the 2 over. And we're so close, we just have to divide both sides by negative 4. That'll flip the inequality for both of these, so now it's greater than or equal to 2. Or x is less than or equal to, 9 over 4. That doesn't reduce nicely. All right. Now, these are actually really close together. If you think about that on the number line. Here's 0. Here's 1. Here's 2. And actually, I'm just going to pause to make sure I did all the math right. I feel like I'm going quick. All right, looks like we're good. So for this one, again, being greater than or equal to 2 is, well, here's 2. There's me being greater than or equal to. And 9/4 is actually just 2 1/4, so it would just be right here and then less than. Now, if this were an and inequality, remember it would be that small little sliver. But because this is an or inequality, this goes back to kind of the first example we saw. We've got everything to the left, we've got the shared part in the middle, and everything to the right. So guess what? Your final answer is negative infinity to infinity. Everything works for this question. Every value will be true for either the first equation or the second equation. And sometimes both of them, but it only has to be true for one of them. Interesting. All right. That's 2.4. Let's dive into 2.5, and then maybe 2.6 will be its own video. Up next, we're going to solve absolute value equations. Absolute value equations are really interesting because absolute values can have two solutions. If I say the absolute value of x equals 5, actually, x can be 5 or negative 5. So absolute values start introducing the idea that there's more than one possible answer. And in case you don't remember, absolute values essentially is asking how far are you from 0. So positive 5 is 5 from 0, and negative 5 is 5 from 0, and that's all you're being asked is what can you plug in to be 5 away from 0? Well, I could plug in 5 to be 5 from 0. I could plug in negative 5 to be 5 from 0. I could either be 5 to the right of 0 or 5 to the left of 0. Two possible answers. Now, when it comes to solving absolute values, there's a few rather, steps. First is isolate the absolute value. Two is create I'm just going to write it like this, other equation. Maybe a better way to say that is create the negated equation. Next, solve both. And 4, check for extraneous solutions. Alright, now we've got some new wordage there, mostly the extraneous solutions. We'll talk about what that means as we go through, but for now, let's start diving into the algebra. So as we solve this out, first, in number 1, my absolute value actually is isolated. So now it's time to learn what do I mean by create the other, or I think I would also say create the negative or negated equation. What that means is, I kind of think about it like this. I'm copying the initial equation as is, but notice I've removed the absolute values. And then the question is, well, what are you going to do with those two vertical lines you just erased? Well, I'm going to take those two vertical lines and I'm going to move them up and over on the other side and write the negated version of the answer that I had before. Right? In fact, you can kind of see that would work right here. If I had absolute value x equals 5, if I just wrote equals -5 on the left, then I got my two answers. It's 5 or -5 over here. So that's effectively what I'm doing right here is I'm saying, yeah, my absolute value is isolated, so I can just say, hey, it could be positive 15 or it could be negative 15. I just don't like writing the equations twice and doing almost the same work. I'd rather be a little bit lazy and not have to write 2x minus 9 more than once, so I write it like this. What do we do then? Well, we just solve like normal. We add 9, but because there's two equal signs, we add 9 to those two other sides now. Careful with your kind of mental math or your calculator math. -15 plus 9 is -6. I've got a 2x in the middle, and 15 plus 9 is 24. From there, I can just divide everything by 2, and I get -3. Notice I'm just kind of bringing them together now. Or I get 12. And I'm going to put a box around them. I'm technically going too quick, but you definitely need to plug these back in and check your work. And I'm going to say that out loud mentally. If I plug in -3, that's -6. If I follow PEMDAS multiplication before subtraction, so -6 and then -9 is -15. And -15 absolute valued is positive 15. I think I didn't say it this way yet, but another way to think of absolute value is if you've got one number in there and it has a negative, just remove the negative, right? So when I said -15 in an absolute value, the absolute value just says, I'm going to make that negative disappear or like it was never there if it was. All right, if I plug in 12, 12 times 2 is 24. 24 minus 9 is 15. And 15 doesn't have a negative, so the absolute values don't matter anymore, and I'm done. Both answers worked. That's why I put a box around it. I knew they would, but we'll talk about when they don't. All right, let's look at number 2. Number 2, now we need to worry about step 1, isolate the absolute value. My absolute value isn't by itself, and we need to ask what's happening to my absolute value. Well, my absolute value has a 1/3 multiplying and a -2 subtracting, or a 2 subtracting. So what do we do about that? Well, we treat this as though, this said 1/3 a minus 2 is 5, and we want to get a by itself, right? Think of this whole absolute value as just a variable. And what would you do? Well, you would add 2 to both sides to get your capital A by itself. From there, what would you do? I would multiply the reciprocal to get rid of my fractions. 3 over 1 is just 3. Now I have absolute value 3x minus 6 equals 21. All right, that's all we're doing in this case. Again, you're just assuming, hey, what if this whole absolute value is just some big letter and I had 1/3 times the letter minus 2? Well, the minus 2 doesn't have the letter, move it over. Then you've got a fraction multiplying, so use its reciprocal. Now your absolute value is isolated. Now you solve like before, so we create that second equation, negative 21 with my 3x and my minus 6 equals 21. If I add 6 everywhere, I'm kind of running out of space. So if I add 6, I get 27. If I add 6 here, I get negative 15. Careful, again, that mental math. And again, all I did was add 6 there, but I'm running out of space. From there, I just need to divide both sides by 3. This time I won't put them both at the same side, but it works the same. I've got a negative 5, and I've got a 9. Again, we should definitely plug these back in to make sure they work, but I'm just going to say for now, trust me, they do. But maybe we can talk about it. Negative 15 is what you'll get when you plug a negative 5. That'll make negative 21. Negative 21 is just 21. 21 times a third is 7. And yep, 7 minus 2 is 5. And we're good to go. If I plug in 9, I get 27. 27 minus 6 is 21. And hey, I've already dealt with 21 in those other numbers, so I know that's going to work as well. So far, no extraneous solutions. I'm saying check for extraneous solutions, but I do know when they'll occur, and I'll make you aware of that before this is over. All right, let's look at the next one here. Be careful with your PEMDAS here, and we've seen situations like this before where we have this 10 minus 3 times stuff. And so a lot of people, their first reaction is to make that 7 and then divide 7 or something. But no. This is essentially its own term, and so you can't make 7 out of this because the multiplication would need to occur first. But remember, we're not actually trying to multiply, and we can't distribute into this absolute value. It doesn't quite work like that. So what are we going to do to make this really clear what's happening? We're going to reorder this, and you're going to see, oh, that wasn't as bad as I thought it was. We're going to reorder this and put the absolute value first. And it's going to make something really clear to us that if it's a negative 3 times that whole absolute value, what's this 10 doing? Well, it's just positive. So how do I write another term that's positive? I write plus 10. So although it doesn't look like it, this 10 was adding to whatever the result of that multiplication to an absolute value was the entire time. So it's just a plus 10. This looks a lot easier to deal with. How do we deal with a plus 10? We move it over to the other side. We get negative 3. Absolute value 3a minus 6 equals negative 16. We then divide both sides by 3. Goodness. And we then have, I guess, 16/3, which is an ugly fraction. But that's okay. We can deal with fractions. We can do it. So what we now have is we have the negative 16/3 on the left. We have our 3a minus 6 in the middle. We have our positive, 16/3 on the right. Now, what are we going to do about that? First, we're going to add 6 to both sides. And I'm just going to write 6 over 1 is equal to 18 over 3. Now, what I'm doing there is reminding you that if I do have to add 6 to both sides, 6 over 1 is going to have to add to 16/3. And 6 over 1 is going to have to add to negative 16/3. But we can only add or subtract fractions when they have common denominators. So what's 6 or 6 over 1 added to something over 3? Well, there's my common denominator. If I multiply this by 3 over 3, I get 18 over 3. So for my mental math here, that's what I'm doing. I'm adding 18/3 to negative 16/3, which is 2/3. There's my 3a. Again, this is me adding 6 to both sides. I'm adding 18 over 3, right? Common denominator, which is 2/3 on the left. I have my 3a in the middle now. I'm adding my 18 thirds to 16 thirds, which, oh gosh, is 34 thirds. And we're almost done there. At that point, the last thing to do is to divide 3. Now, when you divide 3, or when you divide something that was already a fraction, now this 3 is going to the denominator that was already there, and I get 2/9. And we will have more time to review these fraction rules later. Whoops. But just know that if you already have a denominator and you divide something else, it's technically going to end up multiplying with the denominator you already had. You're doing 2 divisions of 3, which means you're doing 1 division of 9, because they'll come together in the denominator and become more than themselves. They'll multiply. All right? Ooh, let's look at number 4. We're making good time. From there, number 4 looks a lot like the one we just did, so I'm going to actually take that thought, right? Remember this one, this 10 out front doesn't combine with the -3 out front that needs to multiply. We reordered and said, oh, okay, that 10's just adding, let's move it. Well, this time, maybe I don't need to rewrite it because I remember that. Again, 10 minus 10 isn't 0 yet. We're not subtracting because the multiplication would need to happen first. What we're saying is this 10 is technically adding. Let's subtract it. Now I've got a -10. I've got my -8k plus 4 equals 0. I now have this -10 multiplying, so I need to divide it. But this is going to be interesting. 0 divided by anything is still just 0. And now, here's where things really get interesting. I technically have -0 on the left. And I've got +0 on the right. But here's the idea. -0 and +0 are still just 0. So I don't actually need the other one this time. Because 0, and this is a rare circumstance, because 0 is what's on the right of the absolute value, you actually don't need a second equation. But it was nice to write it. But again, we're just acknowledging, hey, -0, that's still just 0. So really, I'm just solving one problem here. Really quickly, if you subtract the 4 and divide the -8, you're going to end up with 1/2. All right, I did that a little quick, so let's plug in and check our work to make sure this all ends up being 10. It's also a good review of PEMDAS. So, 1/2 times -8 is, let me think, -4. -4 plus 4 is 0. The absolute value of 0 is 0. 10 times 0 is 0. And 10 minus 0 is 10. Yes, it does work out. I know I said that really quick, but please, please, please practice check. Your absolute value inside should end up being 0. -10 times 0 is 0. So you're just left with the 10 equals 10. All right. Up next, here's number 5. And number 5, spoiler alert, is going to have an extraneous solution. And I can tell you about now when extraneous solutions pop up. What makes this different than the others? Maybe you see it, but we'll discuss it. Now, my absolute value is isolated. So I'm good to write my 2 equations. Now this time though, there's algebra on the other side. Cough, cough, extraneous solution. And because there's algebra on the other side, I don't necessarily want to set up 2 equations, right? Because I need to move some x's around and things like that. What we're going to do this time is, because there's more than one term on that other side, it wasn't just a simple number, we're actually going to do this. We're going to have literally our 2 separate equations here. So there's the line for the problem. Here's the line for the 2 different things we're going to solve here. All right. So what I want you to notice is, again, first you just ignore the absolute values, essentially. Just rewrite the whole problem without them. Now here, I rewrite it, but there's a negative for what was on the other side, right? Here there was a 15, so we wrote the negative version of 15, the negative version of the other side. It was always one number. So here's what the negative version of the other side looks like. It's negative distributed to the entire other side. So it's in parentheses, right? And the negative has to multiply to parts. All right, let's keep going and see what we get. On this side, I think I'll add the 2x just to keep the x positive. And then I can subtract the 10 also at the same time. Looks like I get negative 1 equals 5x. And so x ends up being negative 1/5. All right? Excuse me. All right, for our other equation, we're going to distribute that negative, which would be negative 3x minus 10. Now to solve this, I'm going to add the 3x to the other side because it keeps the variable positive. I'll subtract the 9 at the same time. And it looks like I get x equals negative 19. All right. Now this time we need to check both of them. I out of force of habit, put boxes around them both, but we need to check. And spoiler alert, one of these could or might or will be extraneous. And again, I'll say why after, and we'll verify and just see what happens. Well, negative 1/5 times negative 2 is, well, I guess positive 2/5 plus 9. Now really that's just 9 2/5. So let's see, do we get 9 2/5 over here as well? Well, negative 1/5 times 3 is, well, negative 3/5 plus 10. Now I'm just going to kind of say it out loud here, and you can use a calculator to check, but 9 2/5 is literally just 9 2/5. We don't usually write mixed numbers, but it works. But hey, what if I had 10 and I took away 3/5? Well, guess what? I would have 9 2/5 because I took away 3/5. So this actually works as a solution. Pretty cool. Now let's look at the other side. On the other side, if I plug in negative 19, I get positive 38 plus 9. And then on the other side, I get negative, what would that be? 57, negative 57 plus 10. And that means over here, look what I get. I get 47. And over here, I get negative 47. And it's so close to being true, but it's not true. So negative 1/5 is a solution, and negative 19 is extraneous. Now the question is, how did I know that things were probably going to show up as extraneous? And we'll see this happen multiple times through the course, so don't forget the word extraneous. It's going to pop up again. But extraneous happens essentially, maybe let's say it like this. The funkiest step of this process is step 2 right here. When you create the second equation seemingly out of nowhere, but we're following some rule, but in a sense we are creating some other new equation that didn't exist. When we do that, and there's algebra on the other side, that was the key, because before, if you look at all the examples, when we got to the point where we could make the second equation, it was just a number. Maybe it was an ugly number like 16/3, maybe it was a nice number like just 15 or 21, but in all these other examples, it was number on the other side, now make a new equation. This time it was algebra on the other side and make a new equation. Spoiler alert, that's when extraneous solutions can happen. Also, things to know early on is sometimes when this happens, it could be that both actually still work. It could be that both don't work and there's actually no solution at all. Or it's that one or the other works. You just don't know what you're going to get until you try it out and check. This is why the checking is so important, and we've done it every time, whether we've said it verbally or worked it out. All right, up next for number 6, let's keep on going. We have p plus 2/3. We're just going to add the 1 over and get 8. Maybe I'm just giving you a break after all the stress of what we just went through. And if we subtract 2/3, let's see here. Well, I think this is a good time to practice our common denominators. So if I had this over thirds, that would be 24 over 3. And I would need to subtract the 2/3, because it was added. Over here, this would be negative 24 over 3. And again, I'm subtracting the 2/3. Right? So when it's fractions that need to add or subtract from one another, this was adding, so it needed to subtract on both sides. Or I guess all three sides, so to speak. I then have 8 over 1, but that needs to be rewritten to be over 3. 3 times 3. I had negative 8 over 1, same thing, it needs to be over 3, so times 3 and times 3. And at that point, it looks like I get negative 26 over 3, and I get 22 over 3. And I'm even going to say I'm confident there's no extraneous solutions here because there wasn't algebra on the other side of my absolute value. All right. We've got a few more. And I think all we'll do is, well, actually, we have to go over number 7, so yeah, let's just do it. This time my whole absolute value is being divided by 10. Step 1 is then to actually multiply by 10. And there we go. Now this is a little bit interesting because my absolute value is isolated, but something new has happened that hasn't shown up before. When I create the negated equation on the other side, it's like out of order, so to speak. There's a 10 on the left and a negative 10 on the right. And so maybe I misspoke. You don't need algebra on the other side to create extraneous solutions. Watch this. If I subtract the 4, I get negative 14. Or maybe I wasn't wrong, I just didn't say all the scenarios. Or I get 6. But watch this, if you plug 6 in, that's going to be, well, 10 over 10, which is positive 1. That's not negative 1. If I plug in negative 14 plus 4 is, well, negative 10. Absolute value is positive 10, and 10 over 10 is still positive 1, which isn't negative 1. None of these work, and it's because this is a big red flag. This is your warning right here. If your absolute value is set equal to a negative, there's no solution. So we could have known right here. An absolute value says, what's your distance from 0? What's the positive value that you could be after I take your absolute value? So when do you absolute value something and get a negative? The answer is never. So this is the other red flag to look out for. If your absolute value gets set equal to a negative, or notice the other thing we said here is you should get used to seeing positive number and the negatives on the left. If when you make that second equation the negative isn't on the left, you know, hey, this is one of those weird scenarios where there's no solution. All right, I think for sake of time, number 8 isn't too bad, so I am going to skip it. There's still some fractions there, but I trust you can do it. So let's go to the last section here in chapter 2, 2.6, and we'll solve absolute value inequalities. And here's what we need to know about absolute value inequalities. For the less than inequalities, they solve as and for the greater than inequalities, they solve as or. All right, again, that's the one new step. Now let's see what happens. For the first one, we'll subtract 8 from both sides. We have 2x minus 3 is less than or equal to 7. All right, that's what 15 minus 8 is. Now at this point, we're going to create our second equation where we have our algebra in the middle, kind of the original expression, but instead of making an equal sign, you make the same directioned inequality, so notice that, and you write, again, the negative version. Now this looks a lot like, where is it? I've got it somewhere here. There we go. Number 2 from a little while ago, where I had some inequalities sandwiched by these directions inequalities. That is an and scenario right there. But again, if it's absolute value less than number, then it solves as and. Now let's work this out really quickly. If I add 3 to both sides and divide by 2, I'm actually just going to cut ahead, but I trust you could do that. If I add 3 and divide by 2, we'll get 5 over here. If I add 3, that'll be negative 4. Divide by 2, that'll be negative 2. There we go. That's my and inequality, and we kind of showed you before that you'd have 0, here's your negative 2, here's your 5. One of these is saying x can be greater than negative 2. That's this way. The other is saying x can be less than 5. That's this way. But because this is and, we're only taking that overlap. So this is our final solution. Just that overlap from negative 2 to 5, both with the hard brackets because of the or equal to, or square brackets. All right, from there, let's work on the next one. We have 2x minus 3, and we're going to subtract 8 to the other side. And this says, where can my absolute value end up being less than or equal to negative 3? Now, hopefully, again, this is your red flag right now that this has no solution because there's already a negative on the other side. But let's solve this out and see what happens anyways, even though we should know there's no solution here. Inequality matches, write the opposite version, which is now positive 3. And let's solve, and maybe see why this ends up being no solution. If I add 3 to both sides, do a little more work this time. If I add 3, I get 0. If I add 3, I get 6. If I divide 2, I get 3. If I divide 2, I still have 0. Now let's draw this graph. Here's 0, here's 3. I can be greater than 3. I can be less than 0. Where do those overlap? Nowhere. All right, so it's kind of interesting to see that work out there too. It's almost like another proof of the rule that if your absolute value is set equal to a negative, there's going to be no solution. But that's for the and situation, because remember, if this was or, that would be a little bit different, but this was and. All right, speaking of which, let's go through this one. So we have our absolute value, and we can go ahead, since it's isolated, and rewrite what we had, write the inequality in the same direction, and write the negative version. At that point, if I subtract 7, I get negative 2 over here, and I get, let's see here, negative 12 over here. Let's graph each of those out really quickly. Here's 0, negative 2, negative 12. X can be less than negative 12, less than. X can be greater than negative 2, greater than. And just remember that, again, for interval notation, that's where you would use a union symbol. We might as well do the last one. All right, if I add the 9, that's going to be, let's see here, 23. Again, my absolute value is isolated now. So I copy my inequality, write the negative version, and I subtract 3 from all sides. It'd be 20 over here. That'd be negative 26 over here. I divide the 5 on both sides, or all sides, and I get 4 on this side, and I get, well, I guess negative 26 over 5 on this side, which is essentially negative 5. It's just a little bit further in the negative direction. All right, we've seen this before, but x can be greater than 4 or equal to 4. That's this way. X can be less than negative 26 over 5, which again is just a little bit past negative 5, so that's about the relative space. And that would be our answer. All right. Again, because they can go in different directions when it ends up being an or inequality. So when it's set greater to your absolute, or when your absolute value is greater than the stuff on the other side, That's when you're in an or situation where both sections, whether they touch or not, are valid. But in the and inequality land, they have to match or they have to overlap to be your final solution. And congratulations, that's the end of chapter 2.